All right, hello everyone, and welcome to lesson 2.6. Today we're going to be looking at the very last new topic of Unit 2. On Monday in class, we're going to be doing some review, and then the Unit 2 exam will be for asynchronous work Tuesday afternoon. All right. Before we actually get into the topic of today, which is differentiability, I want to actually return to something that we kind of skipped over earlier this week for time reasons. I want to spend the time, rather than doing it as I do now, to talk about together. And in this question, we want to know, is the graph on the right, that's not the right, on the right, the derivative of the graph on the left? In other words, is this f prime of x and is this f of x? Now remember, to determine sort of the relationship between these two things, we need to remember that for f prime of x, the outputs, or the y values, equal the slope of the original graph. That's sort of one of our rules, right? Or what the derivative actually means as a function. So what I'd like to do to sort of handle this then, if this is our original graph, and this graph, the y values here measure the slope, so presumably when x is 1, the slope of the original graph is 3. Let's start with some really easy slopes. And the easiest slopes to see on a graph are actually the places where we have minimums and maximums. A place where our tangent line, if I sketched it in here, would just sort of skim the surface and stay flat. Now, if you remember from the other class that we did earlier this week, that a horizontal tangent line, a flat line like that, would be a place where the derivative or the slope equals 0. The derivative equals 0. So on our derivative graph, we should have a place, if we go at that x value, which is x equals 0, we should have a y value of 0 on our derivative graph. And at x equals 2, since the slope on the original graph is 0, our derivative graph should also have a y value of 0. So let's check. At x equals 0, is the y value 0? Yeah. At x equals 2, is the y value 0? Yeah. So far, this matches up. Now let's check the other slopes. I like to now think of decreasing and increasing intervals. Notice here along this section, up until that horizontal tangent, our slope is negative. It's always negative. It's negative, negative, negative. Then our slope becomes positive kind of all the way up here, right? Until we get to that horizontal tangent. And then our slope's negative heading down this direction, right? So if our derivative keeps track, if the y values represent the slope of the original graph, up until an x value of 0, we should have a bunch of negative y values. Actually, look at that. Up until x equals 0, our y values are negative. All right, so that seems to match up. Our y values are negative because our slope's negative over here. Our slope becomes positive, which on our derivative would indicate that the y values are positive. Because again, the y values measure the slope of this graph. If the slope is positive, the y values will be positive. Sure enough, they are. And then after x equals 2, our slope becomes negative. So our derivative should have negative y values after x equals 2, and they do. So that also kind of lines up. If we want to verify it, one other thing, the steepest part of this in the positive direction looks around x equals 1. And around x equals 1, our derivative graph has a maximum at x equals 1. Because again, the y value measures the slope of the original graph. And if the slope looks like it has a maximum there, the derivative should have a maximum there. The slope is steepest, the derivative has a maximum. All that lines up. So I'm pretty safe to say that this, in fact, is the derivative of the graph over here. Again, to recap, I start with finding the horizontal tangents, making sure those line up with the x values where I see y values of 0 in my derivative graph, and then check my decreasing, increasing intervals for negative and positive y values on my derivative graph. Just a thought, hold it in your mind. We'll do some practice with that on Monday. Our big question for today, though, is can we always actually calculate the derivative? We have been taking derivatives, but we haven't really paused to ask the question, can we always take a derivative? Can we always find a derivative? And today, we'll dig into that question. Now remember, calculating a derivative really is a limit. It is the limit of the slope of a secant line, and that'll give us the slope of the tangent line. But if these limit definitions of a derivative are limits, just like any other limit, it means that for the limit to exist, the limit from the left has to equal the limit from the right. Remember that from Unit 1? For any limit to exist, the limit from the left has to equal the limit from the right. Now for a derivative, that means something really interesting. The limit from the left is like a slope from the left-hand side. A limit from the right would be like the slope from the right-hand side. And so really what we're saying then, if the limit from the left has to equal the limit from the right, is that if we were to zoom in at that place we're taking the derivative, the slope from the left and the slope from the right have to line up. In other words, if we zoom in, we're going to kind of see a straightish line. The slope from the left and the slope from the right are lining up together. We can't have something where the slope from the left does that, and then the slope from the right kind of juts out at an angle. None of that will be good for us. We want the slope from the left and the slope from the right to be the same. In other words, if I zoom into the graph of f of x at x equals a, we should be able to see that it is locally linear. That I zoom in and I find that if I get really, really close to that x value, the graph looks straight, because then the slope from the left and the slope from the right will be equal. We also need to make sure that it's not an infinite slope, because if you have a place where your graph goes completely vertical, remember a vertical line has an undefined slope, so we also can't have like infinite slopes like that. Now if we put this into maybe slightly simpler terms, what this means in calculus is two things. If we're checking to make sure something's differentiable, that we can take the derivative, we need to make sure that the function's continuous there. And we need to make sure that the function is smooth. Oop, I spelled smooth wrong. Smooth. In other words, that the limit of the slope from the left has to be equal to the limit of the slope from the right. That would guarantee it's smooth, that the slope from the left and the slope from the right are actually kind of running into each other nice and smooth. All right, let's dig into this then. There's really four ways then that a function can fail to be differentiable. We can have what's called a corner. Corners often appear in absolute value functions. Notice here's the graph of the absolute value function, and we have a corner here at x equals 3. Corners are really easy to tell because in an absolute value function, it's going to be the x value that makes the absolute value become 0. But notice here, the slope from the left is -1. And the slope from the right is +1. And so the slope from the left and the slope from the right are not going to be equal there. So our function is not smooth. If I zoom in right there, I'm just going to zoom in on a corner, not a locally linear thing. And so the function is not not differentiable at x equals 3. Now, if I wanted to say this in very official terms, I would say that the limit as x approaches 3 from the left of f of x minus f of 3 all over x minus 3 does not equal the limit as x approaches 3 from the right of f of x minus f of 3 over x minus 3. That would be sort of my official rigorous mathematical way of stating that the function has a corner there. I do this because you actually have to do this on some some free response questions sometimes. Cusps are very similar, but they kind of curve in from the left, come to a point, and then curve out to the right. Cusps are not differentiable. If we zoomed in right there, we would zoom in on like a corner and we wouldn't be able to draw a tangent line. We just kind of have this wiggly wobbly sort of hingy thing. All right, so cusps are not differentiable. So this function is not differentiable at x equals 0. For the same reason up here, I could write the limit as x approaches 0 from the left of blah, 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 does not equal the limit as x approaches 0 from the right of blah, 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 blah. So cusps are not differentiable. We often see them in these sort of fractional exponent situations where we have like a squared or a fourth or a sixth power, an even power over an odd power. We can also run into situations where we have vertical tangent lines. A vertical tangent line is a place where if I drew my tangent line that sort of skims the function here, we get to a place where that tangent line would be completely vertical. And a vertical slope is undefined, right? A vertical slope is infinite, it's undefined. And that is why, if we have a vertical tangent, the function is not differentiable where we have a vertical tangent. In this case, vertical tangents often come up in like cube root functions, and at this function, the function is actually not differentiable at x equals -1, the thing that makes this cube root 0. And finally, a function is not differentiable if there's a point of discontinuity. That's because we need to be able to draw a tangent line. And if we have a discontinuity, like a jump discontinuity or a hole or something like that, we can't just draw like a tangent line. We end up with this weird, like, where do I draw it then kind of moment, right? Therefore, the function is not differentiable. So we got to look out for points of discontinuity. Corners, cusps, vertical tangents, and discontinuities are all the places where functions are not differentiable. The one that everyone forgets about is the vertical tangents, okay? In problems, you would actually generally need to be told there's a vertical tangent if you're just looking at a graph, because it's hard to tell from a graph if there's actually a vertical tangent or just it's really steep. All right, so I want you to take a look at 1 and 2 here, two different f of x, and I want you to identify, based off of what you've just heard, identify all the x values where each of these functions is not differentiable. Pause the video and do that. All right, let's take a look. We have an absolute value function, as we talked about, absolute value functions are not going to be differentiable. So I'm going to say not differentiable. At the place that makes the absolute value 0. So it's not differentiable at x equals 2. Now, if it asks us why, we can't say there's a corner. That's not very mathematical. For corners or cusps, we have to use that sort of limit notation. We would say because the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2 does not equal the limit as x approaches 2 from the right of f of x minus f of 2 over x minus 2. That would be our rationale for why the function is not differentiable. That basically says there's a corner. For number 2, this doesn't look like a situation where there's a corner or a cusp or a vertical tangent. This is a situation where there's a discontinuity. So in this f of x for number 2, the function is not differentiable. Means you can't take the derivative. It is not differentiable at x equals 3. Why? Because if I plug in 3, I end up with 0 over 0, so that's a hole, and that's an undefined element. It makes it not continuous, right? A hole is a gap that's missing, so the function is not continuous. So it's not differentiable at x equals 3, and I would just have to say because f of x is not continuous, I'm going to abbreviate that, not continuous, at x equals 3, and that would be enough for continuity as an explanation if they asked you to explain. All right, I'm going to go ahead and take a look at number 3. F of x's graph is over here, and we're told that f of x has a vertical tangent at x equals negative 2. Identify all of the x values where f of x is not differentiable, and explain why. When you explain why, if it's a corner or cusp, you need to use a limit statement to explain why. All right, go ahead and give it a shot. All right. Identify all the x values where x is not differentiable. Let's start from the left and work our way to the right. So I'm going to say f of x is not differentiable at, all right, working from our left to our right, going to come along, and the first thing I get to is actually x equals negative 2, and I'm told that we have a vertical tangent there, which is why we have to be told that, because it's really hard to tell that that's a vertical tangent. But a tangent line there would actually become momentarily vertical, infinite. So that's actually my first non-differentiable spot. F of x is not differentiable at x equals negative 2 because f of x has a vertical, I'm going to abbreviate stuff just to save some time, a vertical tangent at x equals negative 2. Let us continue. We pass the vertical tangent. Ooh, we get to a hole. That's a discontinuity. So we can also say f of x is not differentiable at x equals negative 1 because f of x is not continuous. I'll abbreviate that also at x equals negative 1. All right, we kind of chug along, we keep going. Oh, we end up with another discontinuity over here. So I'm going to say x equals 2 because f of x is, not equals, f of x is not continuous at x equals 2. We got another discontinuity, so that means the function is not differentiable. And we keep going. Ooh, this is interesting. Looks like we got a cusp or something, and then we're out. So I'm going to say also at x equals 4. And since we have a cusp, we have to use our limit notation. Because the limit as x approaches 4 from the left of f of x minus f of 4 over x minus 4 does not equal the limit as x approaches 4 from the right of f of x minus f of 4 over x minus 4. And there we go. 4 places where this function is not differentiable and why. Now let's talk for a second. We've seen a couple things around differentiability now. 2 important questions. If a function is differentiable, is it continuous? Think about that. Is it? And the answer here is yes. And we say because differentiability implies continuity. But that makes sense because we said in order for something to be differentiable, in order for something to be differentiable, it needs to be continuous and smooth. So if the function is differentiable, it will be continuous. But if a function is continuous, does that mean it's differentiable? Think about that. The answer here is no. A function can be continuous, I'll abbreviate that, but not differentiable. I'll abbreviate that. Think about a function that does that. Can you envision that? A function that is continuous but not differentiable? We've actually already seen one. There's absolute value functions, right? They're continuous but not differentiable because we got a corner there. All right. Let's apply some of these ideas now. Let's use one-sided derivatives, I'll show what that means, to show that this function is not differentiable at x equals 1. Now remember, we said for a function to be differentiable, the slope from the left and the right have to be coming together, right? This is what we call the one-sided derivatives. So to check piecewise functions for differentiability, one of the steps we often do is to actually take the derivative on the left and the right to actually see if they're going to be equal to each other, if they're going to match up. If this function is going to be smooth, the slopes have to be equal to each other on the left and the right hand side of our problem spot. So let's do that. Our left hand side here, 3x, the derivative of 3x is 3. The derivative of x squared is 2x. I'm going to plug in x equals 1. I'll get 3. Oh, but 3 does not equal 2. Since our one-sided derivatives do not match, I can say the function f of x is not differentiable. And I could state that also using those limits we've done before. But f of x is not differentiable. All right. Now another way we could have actually proven that this is not differentiable, they told us to use one-sided derivatives. That's what we did here. Check the derivative from the left and the right against each other and found out that they're not equal, so the function is not differentiable. But I could have also checked continuity, right? Not that if it's continuous it means it's differentiable, but if it's not continuous, well, then we're actually kind of done. And if you look here, for a function to be continuous, the function, the left and the right-hand side, have to be coming together, right? Remember back to Unit 1? And if I check the left-hand side, 3x, against the right-hand side, x squared at x equals 1, they're actually not even going to be equal. So this function's not even continuous. So I could have also checked that. If a function's not continuous, it won't be differentiable. So I could have stopped by checking continuity and saw that it failed and ended there, but it told us to use one-sided derivatives. Let's use that idea here. Let f of x be the piecewise function defined below. At x equals 2, the function is blank. Is it continuous but not differentiable? Differentiable, differentiable but not continuous, and not differentiable. Since we're talking about continuity and differentiability, in these problems, or whenever we're interested in both those things, I like to sort of break this down into 2 steps. 1, we'll check continuity. 2, we'll check differentiability. Well, for a function to be continuous, right, there needs to be a point. So at x equals 2, that looks like it's maybe going to be where we're going to have a problem. At x equals 2, are we going to have a point? Well, if I plug in f of 2 is going to turn out for us 4, so I do have a point. But is the limit going to exist? So I need to check the left and the right-hand side. Is x squared going to be equal to 8 minus 2x at x equals 2? Because that's one of the things we check, remember, that the limit from the left and the right are coming together. So that's going to give me 4 equals, when I plug in 2, 8 minus 4, so 4. Oh, look, the limit exists. The limit is 4. The limit equals the point, so actually the function's continuous. All right. But that doesn't mean it's differentiable. To check differentiability, we need to take the derivatives now. The derivative from the left, the derivative of x squared is 2x. The derivative from the right, the derivative of 8 is 0. The derivative of negative 2x is negative 2. And if I plug in 2, I end up with 4 equals negative 2. Uh-oh. The left and the right hand slopes are not the same. The left hand slope says I'm coming in at positive 4. The right hand slope says I'm coming out at negative 2. So this is actually not going to be differentiable. So the function's continuous, but not differentiable. Not differentiable because the slopes from the left and the right at x equals 2. The derivatives from the left and the right are not equal. So it's just continuous. Continuous, but not differentiable. All right, go ahead and try number 6 on here. Read it carefully and see what you can make of it, all right? Give it a shot. Pause the video, give it a shot, and then check your work. All right, let's see. Interesting question. We have this piecewise function. F is the function defined above. Which of the following statements are true? Does it have a limit at 2, continuous at 2, differentiable at 2? Now this piecewise function is a little different. Let's start with the limit. So if the limit's going to exist, remember for the limit to exist, we don't actually care about what happens at x equals 2. We care about what happens around x equals 2. So let's take the limit as x approaches 2 of x squared minus 4 over x minus 2. Because we don't care what happens at the point for the limit to exist. And this is something that looks familiar, right? We can factor the numerator. If we plug in, we get 0 over 0. We can factor the numerator, x minus 2, x plus 2, cancel some things out, and we'll find that the limit is going to be 4. So the limit exists. It's 4. Now is the function continuous? If the function's continuous, the limit as x approaches 2 of f of x has to equal f of 2. So what's f of 2? F of 2 is 1. The limit we found, though, was 4. 4 does not equal 1, right? So the limit we found actually does not equal the point, so the function is not continuous. Now, if the function is not continuous, then it can't be differentiable, right? Because for something to be differentiable, it has to be continuous. So it's not continuous, we just found out, because the limit does not equal the point value at x equals 2. So it's not continuous. That means it's not going to be differentiable. So the only thing that's going to be true here is 1, so A. All right, go ahead and give 20 a shot. Kind of similar, slightly different. Pause the video, give 20 a shot. All right. Let f be the function given above. Which of the following statements is false? All right, check the limit. Okay, well, we can do that. For the limit to exist, we just look at f of x. The left-hand side has to equal the right-hand side. And it looks like our spot of interest is here is x equals 3. So I plug in 3. That'll give me 5 equals 4 times 3 is 12 minus 7 is 5. Okay, sure enough, the limit exists, so that's all right. I also need to check to make sure the function's continuous. So the limit is 5. If the function is going to be continuous at x equals 3, we need to check the point. Does f of 3 exist? All right, f of 3, I would come to this top one. F of 3 would give me 5. Oh, interesting. The point is at 5. We found the limit is 5. So the limit as x approaches 3 of f of x equals f of 3, which is 5. The point was 5. The limit we found was 5. So our continuity statement here, everything checks out. So the function is actually continuous. The point existed at, and it was 5. The limits found that they were 5. So the function is continuous. Now let's check differentiability. Now if a function is going to be differentiable, right, we need to make sure that the limits of the slopes, in other words, the derivative on the left and the derivative on the right are equal. So the derivative of x plus 2, its derivative, if I took its derivative, would give me 1. The derivative of the bottom, the derivative up here was 1 because the derivative of x is 1, derivative of 2 is 0. The derivative of 4x is 4, the derivative of minus 7 is 0. So the derivative from the left is 1, the derivative from the right is 4, and those are not equal. So the function is not going to be differentiable. The limit exists and it's continuous, just not differentiable. E. Oh, wait a minute. I need to back up for a second. We want to know which of the following was false, right? Sorry, which of the following are false? Always go back to the question. Which of the following are false? So the limit exists, function is continuous, so those are true. F of x is differentiable. That's the only false one. So there we go. Ooh. All right. Go ahead and give this last multiple choice problem a shot. Pause the video and try that. All right, similar situation, right? Piecewise function, is it undefined, continuous, not differentiable, all that stuff. Well, let's check whether it's undefined first. All right, we're interested in at x equals 3. So f of 3, does it exist? I'll plug in 3 down here. That'd be 3 times 6, which is 18 minus 9, which will give me 9. So actually, that's not true. The function is defined. The point is 9. All right, let's check continuity. Continuity, remember, we need to check the limit from the left and the right are equal. So is x squared going to be equal to 6x minus 9 at x equals 3? All right, I plug in 3, that gives me 9. I plug in 3 over here, that gives me 9. Oh, look, the limit exists because we checked the limit from the left and the right. That's what we're doing here. The limit exists and it equals the point. So actually the function is continuous. Interesting. So the function is continuous. Let's check differentiability. So to do that, again, we take the derivative from the left. Derivative of x squared is 2x. The derivative from the right is just 6. And I want that when x is 3. So I plug in 3. 2 times 3 is 6 equals 6. Oh, look, the slopes from the left and the right are equal. So the function's also differentiable. We are both continuous and differentiable. There we go. Now we can also ask some interesting open-ended questions about these derivatives. Given the piecewise function h of x here, determine h prime of 0 or state why it does not exist. Well, we have this piecewise function. We are interested in the derivative. So for piecewise functions, we have to take, if we're going to find the derivative, we need to find the derivative of both parts. So the derivative of 2 sine, derivative of sine is cosine, so that becomes 2 cosine, because the constant multiple 2 stays. The derivative of the plus 1 is 0, when x is less than or equal to 0. The derivative of 2x plus 1 is just 2, when x is greater than 0. So this is our piecewise derivative function. This tells me the slope of this original graph at those x values. Now for h prime to exist at 0, 0 is that breaking spot. If the derivative is going to exist, remember, the derivative from the left and the right have to be equal to each other. And that's especially important since we are interested in the derivative at this breaking spot. So let's check, does 2 cosine of x equal to, setting the two derivative sides equal to each other when x is 0. Well, cosine of 0 is 1, so 2 equals 2. Look at that, actually. The slope from the left and the right are equal. So what is h prime of 0? H prime of 0 then is 2. Since the derivative from the left and the right did agree that at that spot, the slope is 2, h prime of 0 then is 2. If you'd gotten like 2 and 3, then we would have to say the limit as x approaches 0 from the left of and do a whole limit statement thing. But the derivative from the left and the right were equal to each other, so the derivative h prime of 0 is just whatever that number is. This question, I did a similar one on the test last year, and it was one of, if not the most missed question on there. I would keep this idea in mind. And one last kind of thing we can do, open-ended question around derivatives. Let's say we're given this piecewise function. We want to know what values of a and b, if any, would make the function differentiable. This is kind of similar to those questions where we solve for some constant that would make the function continuous. But if the function is going to be differentiable, that means we need to check to make sure the function is continuous. And then possibly, if we still need to, is the function actually differentiable if we can't tell right away. So let's start with continuity stuff. If the function is continuous, That means we should have a point there. If I plug in, it looks like our problem spot we're going to be looking at is pi over 2. So if I plug in pi over 2, do I get a point? Yeah, I'd plug into the top and to give me something. So I have a point there, but for the function to be continuous, I need to make sure that the left and the right hand limits are the same. So let me set the two branches equal to each other. A to the x plus b equals negative cosine of x. And I'm looking at this when x is pi over 2. So if I plug in pi over 2, I end up with a e to the pi over 2 plus b equals, if I plug in pi over 2, cosine of pi over 2 is 0. Now I'm trying to solve for a and b, but I can't go any farther than this. I got one equation, two variables, so I'm stuck. So let me jump over to my differentiability. Let's take the derivative of a e to the x. Well, a is a constant multiple, so it stays. E to the x, the derivative of e to the x is just e to the x. The derivative of b, that b is some constant, is going to be 0, right? Equals negative cosine. I need the derivative of negative cosine. Well, the derivative of cosine is negative sine. There's already a negative there, so I end up with positive sine of x. And I'm interested in looking at this when x is pi over 2, right? So what's the sine of pi over 2? Sine of pi over 2 is 1. So this is a e to the pi over 2, so I'm plugging in pi over 2, equals the sine of pi over 2, which is 1. Oh, I see a variable over here. I could probably set up some sort of substitution. So let me solve for a. A is going to be equal to 1 over e to the pi over 2. So now I know what a is. That's convenient. Let me use that and substitute it in over here. A is 1 over e to the pi over 2 times e to the pi over 2, which was already there, right? Plus b equals 0. Well, 1 over e to the pi over 2 times e to the pi over 2, those will divide away. We get 1 plus b. We don't get 0. They divide away and we get 1 plus b equals 0. So b equals negative 1. And now I found both b and a such that if I plug them in, this function would be differentiable. It would be both continuous and differentiable. Pretty cool, huh? All right. For the rest of the time, this is what I would like you to do. You'll see here on page 40 a problem. It's meant to be challenging. I want you to read through it and give it a shot, as well as trying the review problems on page 41 and 42. You do not need to do the textbook problems. Those are optional assignments. But do the printed work on pages 40, 41, and 42. My answers will be up Saturday. I want you then to correct your work in a different color when you see my answer key. And then upload your work with your corrections to these 3 pages, 40, 41, and 42. Upload your corrected work to the assignment on Google Classroom. Remember, correct your work using my answer key in a different color on Saturday or Sunday. I'll post the answers Saturday. So you'll go ahead and do that. Do those 3 pages. Correct your answers. Upload your work with the corrections in a different color. And then I will also release on the weekend some optional stuff. So that stuff was mandatory. Optional, you can do the textbook problems that are listed here. Always, always good to get that extra practice since we don't have that time this year. And I'll also release some practice for the Unit 2 exam if you want to give yourself a little time to we can do some study work for the Unit 2 exam. I'll release some practice materials. Those are optional. The textbook problems and those practice materials are optional, but pages 41, 42, and 43 and correcting your work is required. All right. Take care, everyone, and I'll see you later.